This presentation covers a description of the zone plate. We describe the zone plate and include a calculation for its focal length. This presentation closes with a comparison between a convex lens and a zone plate. This is an image of the zone plate. A zone plate is a specially constructed screen such that light is obstructed from every alternate zone. It can be designed so as to cut off light due to even-numbered or odd-numbered zones. The zone plate is proof that Fresnel's theory of half-period zones is correct. In order to construct a zone plate, concentric circles are drawn on white paper such that the radii are proportional to square roots of natural numbers. The odd number zones are covered in black ink and a reduced photograph is then taken. In the developed photo, the odd zones will be transparent to light and the even zones will cut off light. Continuing with the description of the zone plate, if such a plate is held perpendicular to an incident beam of light and a screen is moved to the other side to get an image, it will be seen that maximum brightness is possible at a particular position of the screen. Let it be b centimeters from the zone plate. If we demonstrate by XO the upper half of the incident plane wavefront, then P is the point at which the intensity is being considered. B is the distance of P from the wavefront. The radii of the zones are then denoted by OM1 equal to R1 equal to under root of B lambda, OM2 equal to R2 equal to under root of 2B lambda, or in general Rn to be equal to under root of NB lambda, which gives us B equal to Rn square upon N lambda. Here lambda is the wavelength of incident light. If the source is at a distance which is very large as compared to the zone plate, a bright spot will then be obtained at P. This will become clearer when we come to the diagram. We can show that a zone plate has different foci for different wavelengths. As the distance to the source is made large, the incident wavefront can be taken as a plane one with respect to the small area of the zone plate. The even-numbered zones will cut off light and hence the resultant amplitude at the point P is given by A is equal to A1 plus A2 plus A3 and so on to AN where N is odd. In this case, the focal length of the zone plate is given by Fn equal to B equal to Rn square upon N lambda. Thus, the zone plate has different foci for different wavelengths. The radius of the nth zone increases with an increasing value of the wavelength. It is very interesting to note that as the even-numbered zones are opaque, the intensity at P is much greater than that when the whole wavefront is exposed to the point P, as will become clear below. If we add up the contribution to the various zones where n is odd, and if we add up the contributions of the zones where n is very large and odd, we see that the contribution in the second case comes out to be equal to just A1 by 2. We now demonstrate how a zone plate acts as a convex lens. If you look at the diagram and if a parallel beam of white light is incident on the zone plate, then different colors are going to come to focus at different points along the line OP. Thus, the function of a zone plate is similar to that of a convex lens. XY is a section of the zone plate perpendicular to the plane of the paper. S is a point source of light and P is the position of the screen for obtaining a bright image. A is the distance of the source from the zone plate and B is the distance of the screen from the zone plate. OM1 represents the radius of the first half period zone, OM2 the radius of the second half period zone, OM3 radius of the third half period zone, and so on. In moving from one zone to the next, the path difference is lambda by 2. So now look at the diagram. SO plus OP is simply equal to A plus B. SM1 plus M1P will be equal to A plus B plus lambda by 2. Similarly, SM2 plus M2P will be equal to A plus B plus 2 lambda by 2 and so on. In the triangle SM1O, SM1 will be equal to SO square plus OM1 square, both raised to the power half, which is equal to A square plus R1 square raised to the power half. This is using the Pythagoras formula. Similarly, in the triangle OM1P, we find that M1P comes out to be equal to B square plus R1 square raised to the power half. Therefore, SM1 plus M1P equal to A plus B plus lambda by 2 effectively becomes equal to A square plus R1 square raised to the power half plus B square plus R1 square raised to the power of half. Now, if we expand these two binomially, as we will see in the next slide, we can simplify the expression to a great extent. In the meanwhile, all we do here is take A out common in the first expression. So we are left with 1 plus R1 square upon A square. And if we take B out in the second expression, we are left with 1 plus R1 square plus B square, both being raised to the power half. Oh, so the zone plate has multiple foci. As I said in the previous slide, let's expand the previous terms binomially. If we neglect terms of order higher than 2, we are left with A plus R1 square upon 2A plus B plus R1 square upon 2B, and this becomes equal to A plus B plus lambda by 2. So if we take R1 square common, within brackets we will be left with 1 upon A plus 1 upon B equal to lambda, since A and B will cancel on both sides. For the nth zone, this expression is going to become Rn square within brackets 1 upon A plus 1 upon B equal to n lambda. If we apply the sign convention, we will get 1 upon B minus 1 upon A equal to n lambda upon R square, since A lies in the second quadrant and is taken to be negative. And this is equal to 1 upon Fn. Therefore, Fn is equal to Rn square upon n lambda. And here you can spot the similarity with the lens equation. 1 upon B minus 1 upon A equal to n lambda upon R square equal to 1 upon Fn is similar to the lens equation 1 upon V minus 1 upon U equal to 1 upon F. So now we carry out a comparison between a zone plate and a convex lens. The zone plate forms a real image of the object, so does the convex lens. The equation connecting conjugate distances for a zone plate is similar to the convex lens. In both cases, the focal length depends upon the wavelength. However, the chromatic aberration is more severe in the zone plate as compared to the convex lens. The zone plate, however, can act both as a convex and a concave lens. Obviously, a convex lens can perform only as a convex lens. In a zone plate, real and virtual images are formed simultaneously. In a convex lens, a real or a virtual image can be formed one by one only. In a zone plate, the image is formed due to the phenomena of diffraction, whereas in the convex lens, the image is formed due to refraction. The zone plate has multiple foci as we have seen, and hence the intensity of the image is much less. However, in the convex lens, there is only one focus, therefore the intensity of the image formed is much more. The rays reaching the image point through any two alternate zones differ in path by a wavelength or in phase by 2 pi for a zone plate. Whereas for a convex lens, all rays that reach the image point have a zero path or phase difference. In a zone plate, we can use it over a very wide range of wavelengths from microwaves right up to X-rays. But for a convex lens, we can use a glass convex lens for the visible region only. And one last point before we end. You can recall that Newton's rings have radii proportional to square roots of consecutive integers 1, 2, 3, etc. The dark and bright rings have equal areas when monochromatic light is employed. Thus, it is possible to construct a zone plate by photographing Newton's rings as seen by reflected light. That will be all for the ozone plate. Stay safe, stay happy. Thank you so much.